Hello, welcome to video 52 in the lecture Advanced Mathematic Modeling. So in the last lecture we saw the observation by Richardson when he tried to measure the length of the coastline of Britain, and he saw that actually this coastline is not an object which is defined it doesn't exist for itself, because the length he finds depends on the scale, and when the scale goes to 0 the length diverges. So actually the limits of a measurement of the length for a very small scale doesn't exist at all. So the strange thing is that the coastline of a natural object like an island or a continent is not an object that we can describe by Euclidean geometry. And then we saw, okay, we can at least describe the length as a power law, as a function, a power law of the scale with the critical exponent. That's the Richardson exponent, which gives us the roughness of our object. And so we see some intuitive explanation what this roughness means. And now let's relate all of this to the dimensions that we had before. Okay, so let's say if we combine first these two things, so we know the length goes the number of measurements times epsilon, and if we know the length goes with epsilon to minus rho, then we know that the number of objects we need to measure equals or is proportional to epsilon to minus rho minus 1. Or we can say it's epsilon to minus our dimension, and this dimension equals 1 plus the Richardson exponent. Why can we call this here a dimension? Because we said if the number of objects to measure something goes proportional to epsilon to minus an exponent, then this exponent here is the dimension. And we call this the fractal dimension, because this is a number which is then not a natural number anymore, it's 1 plus something. So that's the real crucial thing. So the number of our object goes proportional to epsilon to minus the fractal dimension, and this equals 1 plus the Richardson exponent. So again, the number of objects we need is a power law of the scale. So we have a different power laws, and that's the typical thing. We have seen quite often that if you have different power laws, the critical exponents are related by simple numbers. And now we have seen that the Richardson exponent was in the range between 0 and 1. Yeah? So this means the fractal dimension of a line is 1 plus something. Yeah? So the fractal dimension of a line, fractal dimension of a coastline equals 1 plus Richardson exponent, or 1 plus roughness. And this means, so here this straight line has a dimension, here this smooth line has Richardson of 0, so it has a dimension of 1. This line here has a dimension of 1 plus something. For example, the coastline of Britain has then a dimension of 1.22. And here in the limits where the roughness is equal to 1, then we have a fractal dimension, it's 2. So actually this is already, if the curve is so rough that it totally fills, that's a space filling curve. So this actually is, has a dimension of 2. It's already an area, even though microscopically this is constructed as a line. And so we see objects can have a fractal dimension which is not a natural number. Natural objects have a fractal dimension which is not necessarily a natural number. And if you think this through, if we take an object of our normal geometry, if we take a straight line, take a cube or something, a rectangle, but at first we should say, I mean, we can do the same measurement not only for lines but also for areas and for volumes, and we would get very similar things. And but if we have an and always the dimension that we achieve is the dimension of a natural number plus the rest. And if we have an object of normal geometry, the rest is 0, so the fractal dimension then equals the normal dimension we associate to an object. But if we have a rough line, then the fractal dimension is something which is a real number. So I mean, so like so the coastline of England or Britain is an object somewhere between a line and an area. So the coastline has also aspects of an area, because it has a dimension which is larger than that of a line and smaller than that of an area. And since the dimension is larger than 1, we cannot specify a point on the coastline with a single number. Because if we could specify a point on the coastline with a single number, the coastline would have a dimension of 0, but it does not have a fractal dimension of 0. But so, how is this possible? Why? And that's then suddenly, I mean, or maybe coming back to this, if you see, yeah, this here, if you see such curves and you think on power laws, yeah, and power law, then yes, of course we've seen power laws enough, and then I start to believe, yeah, that's very clear. But then if you think about the consequences, then the consequences are mind-boggling, and the consequences are really against everything we learn in school about geometry. Yeah? Because this means the coastline cannot be a normal geometric object. And one consequence is that we cannot specify the position somewhere on the coastline by a single number. Yeah? And that's then suddenly, oh, why not? Yeah? But think, like, how would you specify the position of this point here? Yeah, here's a small village, or here's a person there. And now I want to give the position of this point with a single coordinate. You could try to make an angle. But if you make an angle, and then the problem is, depending on where you are, and you make a straight line from a certain origin to the points, you can have several points on the coastline which fall on a straight line. So it's not possible to describe the point by an angle, because the angle, the line with a certain angle will cross the coastline at several points. Then you could say, yeah, but then just take the length of the coastline from origin. Let's say here's person A, here's person B, and then the single coordinate would be the length of the coastline between A and B. But we said before, the length of the coastline is not defined, it's infinite. Yeah? And so we do not have a single number which we can quantify this one position. That's very different in a circle. In a circle we just can take either the length of the line on the circle, and in the circle it's defined, or we can take an angle. But for a coastline we need two coordinates. We need one coordinate, the latitude and the longitude. Yeah? So that's suddenly the strange consequences. Yeah? Higher dimension means we cannot specify a point by a single number. Okay, and now let's think a little bit more. Where does this actually come from? What's the mechanistic reason for this this phenomenon? Maybe let's look first again at this main curve, so that, because that's the observation. I mean, this curve means we have an increase of the length at all scales. So if we somewhere here and we reduce the scale a little bit, we have an increase of the length. So the mechanistic origin of all of this is we have an increase of the length of our object on all scales. Where could this come from? So now let's take a simple object of our normal geometry. Let's take a circle. And the circle has a certain length. Okay, and now we do some deformations. We try to deform the circle, which looks more like a coastline, and we can do this. We make a deformation at a certain scale. Deformations or some irregularities. At a certain scale, and that's why we make here some baits. So now we have this object here, and if you look at this object at large scale, so if you measure the length and you have scale which is larger than the typical half circles we put in here, we would have the same length. But if now we take smaller scales, then we see the length is increased. So if we now would plot the length of our object, log L, as a function of log epsilon, then we would see at a large, so that's of course a normal object, the black and the red line here, and they have all length. And when we have a large scale, we measure here the typical length, that would be L, the length of the circle. And now if we come to the size here of these half circles, suddenly we see the length is increased, and on a smaller scale we have a larger length, because we have to take in the length of all these half circles. So this means this object here has a different length, so the length of this object is different depending on a large scale or if we have a small scale. Yeah? And so why did the length increase? Because at a certain scale here, and this was this scale here, there were some irregularities appearing. So if we reduce the scale, we observe these irregularities, and this led to an increase in the length. But then, if we reduce the length, the scale smaller and smaller, nothing happened anymore, because the whole thing then was smooth. But now it means if we have a fractal, this means if we now go to a smaller scale, we could of course have something like this, that we have here a lot of smaller things happening here, and so on and so forth. And then we would have, at a certain scale, we would have again an increase in the length at the scale of the blue circles. And now in a fractal, this means these increasing lengths should appear on all scales. So if we have a fractal, the new irregularities appear at all scales. So meaning, if we look again at our coastline, then the coastline will have some very big irregularities, big baits. And when we zoom in, it has some smaller irregularities. And when we zoom in more, it has some smaller irregularities. And it can never stop. Yeah? So the better we look at the system, we always identify new irregularities. And these lead to an increase in the length. So new irregularities appear in all scales. And now the interesting thing is, I mean, this would just mean we have a line which is increasing, but now this appearance is uniformly on all scales. And that's astonishing. It's a power law. Yeah? So it could, in general, it could be anything. Why is it a power law? But that's the observation. Yeah? So this appearance is uniform at all scales. So this means there must be something happening, because at first there's no reason why this should be like this. But if this appearance, this increase in length, is the same at all scales, then we can put all this together in a single number, the fractal dimension. And then we say such an object, it is self-similar. Because if you take a small part of the object and zoom it out and increase it, it will look the same, because the appearance of irregularities was the same at all scales. So self-similar object looks the same at all scales. Because the irregularities are built into the system, exist at all scales in the same magnitude. So this self-similarity of geometric objects, that's the hallmark of all fractals. And this applies not only for coastlines, but many different natural systems. So if you have a furrow in the field here, at a very small scale, this looks somehow the same as the Grand Canyon on a very large scale. And that's the strange thing. Why should it be like this? But if you have a self-similar object and the irregularities are the same at all scales, if you look at the system, you can, by looking at it, not detect if you have a picture of the Grand Canyon. So you're looking at maybe 100 kilometers or tens of kilometers, or you have this furrow in the field and you look at this at the order of centimeters. The same for a cloud. A cloud can be a very small piece of fog in the air, or it could be a huge thing over hundreds of kilometers. Yeah? And so that objects look the same or have the same roughness or same structure at different scales. That's the self-similarity. Yeah? And that's the deciding thing for a feature of a fractal. And I mean, as I said, like the main observation that something like this can exist in nature, this was due to Richardson, but it was Benoit Mandelbrot who really made this famous and exploited this in detail. And he has this beautiful book, The Fractal Geometry of Nature. And so this book appeared in, it was 1982, but so like the first publication by Mandelbrot about this was 67. And so he said that he generalized these fractals to geometric concepts of many different objects here. So like the fractals were now a new paradigm. For the geometry of natural objects, because natural objects are always rough, irregular, and self-similar. At least self-similar in a certain range of scales. And so Mandelbrot, then he said this famous things that clouds are not spheres, and mountains are not cones. And so what Mandelbrot basically said, that we learn in school the classic geometry, which has not so much to do with the reality of physical objects. And now when you look at nature, you see fractals everywhere, and then maybe we have to distinguish a little bit fractals in nature. So I mean, first you have to look at what do you have if you have objects that have a fractal dimension which is smaller than 1. So objects which have a fractal dimension of 0 point something, and this is often called dust here. And fractal dimensions like this is if you have a clustering of points, but when you look in a certain area how many points you have, this scales with the radius. So you can have objects which have a fractal dimension which is smaller than 1. And then we have seen objects which have fractal dimension between 1 or 2. So that would be irregular lines. Yeah. So that's here these rough lines. But then you can have objects which have a fractal dimension between 2 and 3. That would be then surfaces, rough surfaces. If you look at the bark of a tree, you find a rough surface, and you can have objects which have a fractal dimension larger than 3. That would be rough volumes. So typically, so what we say, so like if you have an object, so the dimension of this object is an integer number, a natural number of the underlying geometry plus some roughness, so natural n plus some roughness exponent, and so distinguishes if you deal with dust, lines, surfaces, and so on. So for example, now the Grand Canyon would be a rough surface, if you so want, yeah. And now we can look for examples in nature. And you find then a lot. So basically all surfaces, if you look at surfaces, it could be surfaces from ground by erosion. Yes, so like this furrow in the we had before, or the Grand Canyon or something, or the surfaces of mountains. Mountains, the bark of trees. If you look more carefully, if you zoom in on the surface, it will always be rough. But also when you have corrosion, or in industry, if you have wetting of surfaces, or if you have a CD even, and you put substances on to encode information or produce surfaces in industry, you find rough surfaces. When we go in geology and you want to know like the deposits of minerals or oil, yeah, so that's typically distributed as fractals in the earth. Biology is all abundant from these fractals. All living objects are basically geometrically fractals. But let's just give some examples, like if you have a tree, yeah, so you have a trunk, and then we have first branch, and then we have smaller branches, and from the smaller branches we have again smaller branches. And so here the roughness appears that when we go to along the length from the root to the leaves, we get new branches at all scales. So a tree, or all kinds of ferns and plants in general, have here this fractal structure. But you see such a fractal distribution thing not only in trees or ferns, we see it in the lung or in our blood vessels. Here, where we have the lung, you have your big tube from the lungs, and then you have the smaller vessels, or similar in the blood, from the aorta to the smaller and smaller vessels, where the surface is increased. Actually, now why should you do this in biology? Why should the lung or the blood vessels be like this? And that's the reason, as we were here. Maybe let's write a reason for this. And maybe in a tree, maybe the reason why is a tree like this, it could be either because it's very simple to grow like this. If you have the growth, and if during the growth you have a iterated splitting of new branches, maybe naturally you get a fractal object. But if you want to, like in particular in biology, in anatomy, in the lung or blood vessels, you want to have a large surface, so like for example where you can make really exchange between oxygen and blood. You want to have a huge surface. But how do we get a huge surface? And then you see, we know biology can exploit this. Here if you have the length of a curve, and if for some reason you want to have a length which is really huge, it's incredible, you just need a fractal dimension. And now it depends on which scale does the chemical reaction take place. If the chemical reaction, the exchange of gases, for example, takes place at a very small scale, if you have a fractal object, you can pack in a huge size in a very small compact thing. Like for example, if you have something like this here, if this would be a surface of some interface, and at this interface a chemical reaction can do, if you have the same absolute scale, let's say of 1 meter, and then here you would have a very small reaction surface, and here larger, and here an even larger, so you can have basically an infinite large interface where increasing the reaction rate enormous. So biology exploited this by producing these fractal regions in anatomy, because we can increase the effective reaction surface. Similar for in our brain, like if you look the outer brain, so you have this in the cortex you have this very fractal geometry, so you can plug in a lot of effective surface in a small brain. Now such things here like this objects with iterative branching, you see as networks in many systems, like in technological networks. But also again in geology, in river networks. Take a river here, so here's the sea, so you have here the river, and so from the river at certain points you have smaller rivers, and then even smaller streams enter the whole thing. And so like you have again a fractal structure of all the stream system until you go to the ocean, which has here a fractal structure. Again, this video is getting a bit large. Let me make one final remark also, like in art and architecture. So, and okay, that's not really scientific, but did you ever wonder why, if you have a wall from concrete, and you have a wall like this, and it's just gray, why such a house looks boring or not so nice, if this is a house? Yeah. And when you compare it to a natural living system which has looks more beautiful, then why does the house looks boring? And I would say because there is not so much information for the eye, because you just get one information. But now let's try, you want to make the house more interesting, so that's again here the wall of the house. And let's now say we start to make a little bit, we put in some windows. It looks already a little bit better. But let's say we make now some structure in the house because we have bricks here. Maybe it looks again a bit more interesting. And now we put in some flowers here in the windows, and maybe here some flowers before, and suddenly you have some more information, and suddenly the structure looks more interesting, because depending on the scale which you look at, you have more and more information plugged in, and so it starts to look more natural and more interesting for the human eye. And so that's maybe for me a reason why this concrete walls look so boring. There's not so much information. And so you can now exploit this in architecture. If you want to have something interesting, you can try to generate some surfaces or objects where you just put in information in all different scales, and suddenly it looks natural. And this is exploited in movies nowadays, when you cannot like for example, science fiction movie, you want to have a planet which should look different, and you want to have some nature landscapes there. We can generate such fractal landscapes in the computer by putting self-similarity in some landscape, and suddenly this looks for the eye very natural. Yeah. Maybe that's all I want to say in this video, because the video is getting already rather large, and maybe we will make another video about fractals, where we see how we can construct fractals mathematically, and how we in practice measure the fractal dimensions of such natural objects. Yeah, but this we will do in another video. For the moment,